Great, thank you so much for everyone's patience. We're going to begin the broadcast for today's Veolia Water Tech Talk entitled Water Conservation and Its Effect on Wastewater Treatment. My name is TJ Willits and I'll be your moderator for today's broadcast. We just have some housekeeping items to go before we begin the technical portion of the broadcast. Just some things related to the audio. There's two ways to listen into the audio broadcast for today. You can log in using your computer audio, which is probably the best quality. If you have any issues with that, you could also switch and toggle over to a phone call. And the phone call method will allow you to log in like you're logging into a conference call. Just want to let everyone know that today that their microphone is automatically muted. There's a lot of people on the call, and that this broadcast is being recorded and it'll be available to you via email within 24 to 48 hours after the live event. Now, everyone's microphones are muted, but we want to make today's broadcast as interactive as possible. So what we're going to do is have a question and answer session at the end of the broadcast for as much time as allows. To go ahead and log your question, go ahead and put it into your chat box, the question chat box. It should be on the right side of your screen there. And we'll just queue as many of those up as possible and get to those questions at the end of the broadcast. Now, today is our Water Tech Talk on water conservation and its effect of wastewater treatment. We have some upcoming webinars as well that we want you to make you aware of there. If you wanted to grab that QR code on the screen, you could go ahead and hit our website and log in and register for any of those upcoming webinars that we have. We have one on April 2nd related to discovering the game-changing advantage for cold WFI technology. That's related to pharma. And then also we have a webinar for distilleries called Getting into the Spirit of Sustainability. So something to look forward there for our upcoming Veolia Water Tech Talks. Now, in addition to the live webinars that I just discussed, we have several webinars available on our website that you could go ahead and log on and watch on demand at your convenience there. And the website address is veoliawatertech.com. And if you would like a participation certificate for attending today's broadcast, no problem. We're going to email that out to you a day or so after the broadcast that you could use for your continuing education credits if you wish. Something fun, after the webinar, we're going to have a chance for you to log on and take a survey. Your feedback is really important to make sure that these broadcasts are as valuable as possible for those in attendance. So for anyone that takes the survey, we'll enter you in for a drawing for a $25 Amazon gift card. So that'll pop up right when you leave the webinar. Take about 30 seconds and fill that out. That'll be information that we'll look over and use to improve future broadcasts. Now, a little bit about Veolia Water Technologies. What we do is we have a core capabilities that span projects, product technologies, services, and chemicals, and we provide these areas of expertise to several key industries. Today's broadcast will be mainly related to food and beverage or some industrial type of facilities that you'll be learning about throughout today's broadcast. But we do have an expansive amount of experience in many different industries, as you can see there on your screen. Now I'm looking forward to introduce you to our two panelists that you'll hear from shortly for today's broadcast. First, you'll hear from Ryan Johnson. She's a large projects business development manager at Veolia Water Technologies and Solutions. Ryan has worked in the industrial water field for more than 22 years, and her focus has been mainly in the biological space of anaerobic and aerobic treatment, with a focus on water reuse technologies as well as biogas utilization. Joining a little bit later in today's broadcast, you'll hear from Christina Gerber. She's a domain leader for anaerobic digestion. And Christina, she's been with Veolia and within the biosolids and wastewater industry for over 20 years with a BS in chemical engineering, an MS in engineering management, as well as a professional engineer. She started out as a pilot and lab tech, with her career path exceeding the project engineering, project management, proposals, and now technically supporting the various teams across Veolia. So at this time, I'd like to hand the webinar over to our first panelist, Ryan Johnston. Are you with us, Ryan?
I sure am, TJ. Thanks very much for the handover. Appreciate it.
Thank you.
Let's start by taking a look at our agenda today. We want to touch base on the sustainability of just the food and beverage industry as a whole. We will talk about some of the sustainability goals that the different corporate organizations have, and hopefully what some of your organizations have as you continue to move forward through 2025 on to some other organizations that have goals through 2030. We're going to look at some water management challenges that I know many of you are facing, and then we want to overcome wastewater intensification. And how do we do that? What technologies do we do that with? How can we better help you to reuse water, reuse biogas as we go forward in your facilities? And most importantly, how do we get started with one of these wastewater projects? So we'll touch base through a quick high-level checklist that might be able to help with some of your water needs. So sustainability in the food and beverage industry, again, we're going to touch base on some of these. Why are we here today? What organizations are we looking at? So there's growing interest in sustainability approaches in the food and beverage industry. There's recycling water. Recycling organics can allow a company to reduce your carbon and water footprints. Many customers like you are increasingly setting ambitious sustainability goals, which can be more and more challenging to achieve as low-hanging fruit has already been implemented at your many different facilities. Techniques and technologies to achieve further water and carbon footprint reduction will be the further topic of the webinar today. So you can see the Sustainability Development Goals chart to the right. Based upon the United Nations Sustainability Development Goals for 2030, Veolia's mission statement incorporates 3 pillars of this. We want to combat pollution and accelerate ecological transformation. We want to support the development and commitment of all our employees worldwide. And we want to support the development of territories in a more responsible way. Veolia's focus is on developing solutions to help clients meet their industrial goals, as well as returning money to its shareholders and making sure that organizations are profitable as they do it. So let's look at some of the industry commitments from some of the major top 100 food and beverage producers. You can see in the center bars, goal 1, 2, and 3 come from Coca-Cola. They're looking to achieve 100% regenerative water across 175 of their facilities by 2030. Many of the projects that they are looking at implementing and are in the process of implementing are going to help them hit those high targets that they're looking to achieve. Cargill, another partner, has a long-term water commitment as well. They want to implement water stewardship at more than 68 priority water facilities across North America and around the world. So again, staying with the beverage industry, Keurig Dr. Pepper, many of you are probably having some of their drinks as we speak, is looking for 100% to partner with their highest water risk operating communities to replenish 100% of that water that's used in their beverages by 2030. So you can see lofty goals by some of the major organizations. If we shift more to a food standpoint, Saputo and Campbell's, again, both have lofty sustainability goals. Saputo looking to target significant and sustainable progress by 2025. And then one of the major drivers within the industry for our food and beverage partners is Walmart. They have a supplier sustainability assessment that they issue that's been driving sustainability in their supply chain. It requires many suppliers to define and meet their sustainability goals, most importantly to determine the prime shelf space within their stores. You can see from the big 50% on the chart, 50% of the global population can already be living in areas facing water scarcity, even as quickly as this year. So water is a key raw material, obviously, in the food and beverage market and becoming more and more important. So how can we target water reuse, and what are some of the common challenges that we're seeing for food and beverage producers? Some of the common challenges are POTW stress. Many of our food and beverage producers are seeing high sewer surcharges, major modifications to their discharge permit, whether COD and BOD intensification is lowered, adding TDS permit modifications, many different drivers for our food and beverage producers. So in addition to the sustainability goals, we're seeing these constraints on wastewater regulations and compliance. So how do we manage all these different challenges and still make money? We have to juggle all of these components: corporate sustainability, water stress and scarcity, water regulations, and making money for our customers. So over the next couple slides, Christina's going to talk through some of the different technologies that can be incorporated and what some of the water management challenges and the strategies for sustainable water and wastewater management can be. So if we move ahead one more, we can look at the common water management strategies that many of you are implementing already. Certain water mapping, audits, metering have been implemented. An easy one that you can tick off as low-hanging fruit is certainly employee training and behavioral analysis of your staff and your teams. Then we start to move into water efficiency. How can we look at water reduction across the plant? And then into water reclamation. Where can we potentially reuse some of this water? Non-contact steams such as boilers and cooling towers potentially are targets for water reuse that we'll talk a little bit more about as we go through the different slides. So what is the impact of increased sustainability and the circular economy on wastewater? So this slide is a traditional production facility where you can see the potable water comes in, many times goes through RO system for, and becoming a raw ingredient within production, and out comes the finished products, and waste and recycling many times go out in a truck or are sent out through a facility wastewater treatment system to a POTW. This has been the traditional course of action within a food and beverage production facility. Now, many of our customers and our partners are teaming up to have different add-ons to these facilities to get more out of their waste products. So again, Christina will talk through some of the different technologies. If we look to incorporate an anaerobic wastewater treatment system, we're going to develop a green usable biogas that can be used in many different ways, whether it's pipeline quality or offsetting natural gas within your facility, or even electricity production. It's giving us a value for wastewater treatment. We also have depackaging and recycling systems. We can send off those particular materials. It gives the opportunity to recycle any return products and give us the ability to, again, produce usable green biogas. After an anaerobic system, we have aerobic polishing, which would precede an RO. That RO is going to give us the ability to reclaim anywhere from 80 to 95% of that water back in production. So a lot of unique spins on a typical wastewater treatment facility to give more value to a waste product in green energy and reclaimed water. So as we look at the impact of the increased sustainability and the circular economy on wastewater, you'll see many of these things that are driving it is the wastewater intensification. Many food and beverage producers are having a much higher BOD and COD organic loading that's coming out of their facility, increased total suspended solids, and then a major driver that we have seen in the last 2 to 3 years is increased total dissolved solids or salts in the facility, and that is going to require much more waste treatment, potentially to handle brine from a UF and an RO. So with that, I'd like to transition to Christina so she can talk through the technologies on how we can go ahead and overcome the wastewater intensification. Christina?
Thanks, Ryan. So like Ryan had mentioned, the increased TSS, increased COD and BOD are things that manufacturers are now having to worry about. Rather than just sending it down the drain, these types of constituents have to be treated. So the key areas for wastewater treatment, Ryan touched a little bit on this, but we have depackaging. This can be when you have a food to waste digester, recycling coming in, you can depackage it and send that through the treatment, the wastewater treatment. Then you have a primary section, which is usually DAF, screening, any kind of big items coming out of the wastewater to try to get it into a uniformed flow forward into the biological systems. You also have some EQ, some pH neutralization, and any clarification. The main step are the biological steps, and these are removing the BOD and COD. As Ryan mentioned, I'll be talking about the anaerobic section, but this also incorporates the aerobic treatment as well, which can also reduce COD, BOD, and reduce nitrogen, phosphorus. And then there's tertiary polishing. Tertiary polishing are disinfection, microscreens, disc filters, any kind of clarification that is needed after an aerobic system. Then also there's water reclamation, any kind of UF, RO, and then sludge handling and brine treatment. I will touch upon the biogas utilization as well, creating these wastewater treatment facilities into energy positive. So the first section is the high performance anaerobic technologies. And this is really just transforming waste into energy while reducing the BOD and COD. So anaerobic treatment 101, there are three main steps that happen in the biological treatment. You first have hydrolysis, which is essentially breaking up of the organic molecules. And then you have acidification, which is taking those smaller molecules and turning them into fatty acids. And then you have the third step is methanogenesis. This is where it takes those fatty acids and creates an energy in the form of methane. This is the overall mass balance of a generic anaerobic system. If you happen to have 1,000 pounds of COD going into an anaerobic reactor, typically you have about 80 to 90% COD removal. Obviously, it fluctuates slightly between what the constituents are going into it, but 80 to 90% is essentially what we estimate in the beginning. Now, with that said, there are certain pieces and parts that can intensify that, but for right now, for this purpose, we're going to say 80 to 90% removal of COD. From that, though, biogas is made, and this is where the sustainability goals of a lot of customers come into play, where you can create this green energy from an anaerobic system. It is important to note that the anaerobic system is a roughing step. It will not get down to tertiary treatment. That's where you need to add some additional pieces and parts on the back end of an anaerobic system. The biomass that is created from the anaerobic system is about 10 to 12 times less than an aerobic system. So you can already see the benefits not only of creating an energy, but also reducing your hauling costs for any type of waste from the system. Now, the high rate systems have granular sludge, and that is something that can be used to seed other anaerobic systems. That could be a potential revenue stream as well for the anaerobic facilities. So here are the just a high level view of the different types that are out there. You have high rate systems. This is meant to be more for the soluble COD, BOD systems. These are your sugar wastewaters. It does have a lot of food and beverage, brewery waste fit into that category. I would say the biggest thing is the TSS cannot be too high, the total suspended solids. That's where you would bump into a medium rate if that was necessary, if the high rate systems, if there was too much TSS going into a high rate system. The next up is the medium rate, which is the anaerobic MBR, the anaerobic SBR. These are a little bit, they are loaded slightly less than the high rate systems and therefore do have a slightly bigger footprint. The anaerobic MBR is essentially taking a CSTR, which is a low rate system, and coupling it with membranes on the back end, and you recycle that solid stream back into the tank, which then decouples the HRT and SRT allowing your food to mass ratio to be slightly higher. And then the low rate system is a typical CSTR, which is a continuously stirred tank reactor. This is just a tank that is mixed continuously, and it is meant to hydraulic retention time on ballpark of 20-ish days, as where the high rate system is the HRT is usually in terms of hours rather than days. And then there also is some biogas treatment that is available, the sulfothane and the MEMGAS system. It is important to note that these are biological systems, which means that the correct pH, it likes to be neutral pH, temperature, it likes to be body temperature, and then the correct F to M ratio is there. So you have the food to mass ratio and you're feeding your bugs appropriately for what they need. The high rate systems, I mentioned earlier that they do have granulars in them, and those granules are actually separated by a three-phase settler. That three-phase settler, it separates the sludge granules from the effluent and the biogas. So all anaerobic technologies create biogas. Biogas is approximately 60 to 65% methane, which is where the value of energy comes from. So that is actually what you're trying to capture and what you're trying to utilize as this renewable energy. The remainder of it, the remainder 35 to 40%, is typically carbon dioxide it's saturated with water vapor, and then it has trace amounts of impurities. Now those impurities can be H2S, hydrogen sulfide, which it does depend on what the substrate coming into the anaerobic is. If it has high sulfate coming in, you will have slightly high H2S coming into the biogas. But you can see that with the different substrates, it could be industrial wastewater, it could be municipal sludge, or like I mentioned, it could be more of a food waste energy plant where you have organic waste coming in. So the constituents of the biogas do depend on the substrates coming in. But that raw biogas has 60 to 65% methane and that is what you're trying to reclaim. There are multiple different options for the biogas usage. I would say 40, 50 years ago, people flared the biogas. Every anaerobic digester has to have a biogas safety flare on it, and that safety flare will, it burns the biogas to not release it into atmosphere. But people then started realizing that the biogas had value to it, and they would put it into biogas boilers. Now this boiler is a natural gas boiler with a biogas train on it. It is simply meant to burn at a lower BTU value on that train rather than the natural gas train. And then I would say about 20, 25 years ago, people then, wastewater treatment facilities started putting it into a CHP, which is an engine. It's a combined heat and power. And this would create electricity as well as heat that could be utilized in the main facility. This is slightly more cleaning or biogas conditioning into the CHP. The CHPs like less than 200 parts per million of H2S going into it. And so you do have to clean up a little bit of the H2S, and you do have to remove moisture. And then lately, over the past 5 to 10 years, we're seeing a lot more manufacturers turn to biogas upgrading. And this is where a revenue stream can actually come into play for the facility. As I mentioned, methane is about, so the biogas coming into the facility or out of the facility is about 65% methane. And what we need to get it into a natural gas quality is about 97, 98%. So what biogas upgrading does is it removes the all of the impurities from it to get to the natural gas quality. So the treatment process of that is, the first step is usually drying, but depending on the H2S in the biogas, you might have to do a bulk desulfurization, which is kind of a roughing step to get out the H2S. So if you do that, you get it down to less than 100 ppm of H2S. Then it goes into a drying process step, which removes the H2O and the ammonia. Then there's an activated carbon filtration, which removes all of the impurities. That polishes the H2S down to about 4 ppm, and it removes any VOCs and siloxanes in the stream as well. Then you get to a compression step, and this compression step is, it takes the biogas at approximately, coming out of the digester is in terms of inches of water column, and the compression step takes it up to 200 to 250 psig. So that compressor compresses it, and it sends it through some membranes, and these membranes are, it is a 3-stage process with Ovonic membranes. Stage 1 takes it from 65% methane up to approximately 85% methane. And now, as I mentioned before, the quality of natural gas is about 97, 98. So stage 2 gets it from the 85 all the way up to the natural gas quality. From that, you have 2 reject streams, and these reject streams are high in CO2. And the first stage has a about 5% methane in it as well. That cannot be released to atmosphere. So what we choose to do is put a 3rd stage of membranes on, and this polishes that reject up down to less than 1% methane in the off gas. So you can see that 2 stages are necessary to get it to the quality of natural gas, but the 3rd stage actually recovers up to 99.5% of the methane yield. So you'll have low methane slip through the system, and depending on your location, it in New Jersey and California and Ontario, they require less than 0.5 or potentially a thermal oxidizer on that off-gas stream. So depending on the location of your facility, this is something that can be utilized. So then we talk about a case study that is an anaerobic wastewater treatment facility. This is a chocolate manufacturer in Pennsylvania, and their goal was to get their wastewater. They had an outdated wastewater facility, and they wanted to do better than the sewer surcharges that they were going to be imposed upon. So their goal was to get less than 10 ppm of BOD, less than 10 ppm of TSS, less than 5 ammonia, less than 2 total phosphorus, and the influent was approximately 720,000 gallons a day with a COD of about 5,000 milligrams per liter. But you can see that this actually is a perfect system for a high rate anaerobic digester. So the treatment flow train was screening. Then they had EQ to iron out the peaks and valleys of their production facility. The anaerobic digester, which is an UASB, it's an upflow anaerobic sludge blanket. The biogas goes to a gas holder through a sulfothane to clean it up, and then goes to a CHP. The wastewater then is further treated by an aerobic MBBR. The DAF removes the TSS that it builds up in the aerobic system, and then you have a disc filter and UV. So the results of this project actually are a very high quality effluent. this is an energy positive plant, and because the wastewater effluent is actually cleaner than what the city sewer requirements are. But this customer chose to invest in their future for a potential water reuse system. And then also they sort of changed the way that they looked at it. Rather than a wastewater treatment facility, this actually can then turn into a wastewater reclamation facility. The nice thing about this is that it does produce 6.5 gigawatt hours of green electricity annually. So here is just a photo, and you can see the footprint of all of this. You have the sulfothane scrubber, which is the tower. That is a chemical wash system followed by a biological regeneration of that chemical. You have the UASB, which is the tank in the center, and the gas holder right in the front, that's that bubble. That gas holder simply just irons out the peaks and valleys of the biogas production and going into the CHP. And that's the container, the black container is the CHP system. And then the enclosed flare is off of this picture. So with that said, this was just one facility that had an MBBR. Next up, Ryan is going to talk about the aerobic NBR. Ryan?
Thanks, Christina. I appreciate that. So as Christina talked through the last case study, you understood that there was an MBBR, but now there's also an alternate aerobic technology that we can look at for even a more pure effluent on the back end. And that's an aerobic MBR. It's a membrane bioreactor and the preceding step before an RO system for water reuse. So as you can see, it's for biodegradable wastewaters. It's for high COD, high BOD wastewaters, and it can also be used in anaerobic polishing to follow the steps that Christina talked about previously. And again, it's a pre-treatment step for the reverse osmosis system so that we can reuse and recycle water. It's a small membrane tank that's going to have the membrane cassettes, and you can see in the picture on the right, those are actually craned into place, and there are multiple cassettes that can be added up and kind of developed on a modular basis as you expand the facility to treat anywhere from a couple 100,000 gallons a day all the way to a couple million gallons a day of wastewater treatment. It's all major equipment that you've seen on many of your other facilities, pumps, VFDs, membranes, air scour, aeration. It's not any unique technologies, but the way that it's structured together is what makes it unique. This slide will show us the major pieces of the MBR. So number one, you're going to have a biological reactor. That's actually where all of the sludge is. It's where your blowers are going to send their air, and your biological sludge is actually going to degrade all of the BOD and the COD in the wastewater. Then the material is going to be pumped through a set of membranes, and the membranes are going to pull a vacuum on the water. You're going to have the outside dirty material, or excuse me, the dirty sludge material on the outside of the membranes, and you're going to pull a clean water through the membranes that can be reused. Small control panel, and then permeate and air piping, and a permeate pump and air blowers. Again, not a lot of pieces of equipment to get a very pure effluent on the back end. So what are some of the advantages of an MBR? Most importantly, its footprint. If you look at a major conventional activated sludge system versus an MBR system, which you can see in the box on the right, the conventional activated sludge system is outlined by the red box, and the MBR footprint is outlined by the blue box. And you can see that the MBR itself is nearly half, if not a little less than half, the size of the conventional activated sludge system. When you're looking at already integrated wastewater treatment plants to food and beverage production facilities, there's not a lot of extra wasted space to incorporate wastewater treatment. So footprint is certainly an important factor. More importantly than even footprint is the reliability and the quality of the water that you're going to be getting out. With the UF membrane, there is a physical barrier that is consistently producing high quality water. Your TSS coming out of this is less than 5 milligrams per liter. Your BOD in most cases is less than 10 milligrams per liter. So that is going to be well under all of the sewer surcharge limits, and it will be the perfect pretreatment for an RO system that we'll talk about in just a second. They are conventional equivalent life cycle cost to that of an aerobic, conventional activated sludge plant. So now, if we want to focus on water reclamation, we come to a reverse osmosis system that many of you have within your production facilities, whether you're getting water in from a town or a well, you send it through the RO system before using in your production. This is the same sort of system, just developed for wastewater. So you're going to have your anaerobic system, potentially followed by your aerobic system, your MBR, and then it would be paired with the RO system. So we have a Veolia ProFlex reverse osmosis and nanofiltration system. We have delivered more than 1,000 of these installations around the world to many of the top 10 food and beverage producers around the globe. This will give you the ability to recover up to 95% water that you send down in your particular wastewater stream. So the key to successful operation of the RO system is to be able to provide a good, consistent UF quality. So preceding the RO, again, we talked about the MBR. It's going to give us low turbidity, low bacteria, and low residual organics, low BOD, low TSS. So that gives us the benefits to the RO, protection, the membrane protection from particles and biological fouling, and it gives us the ability for a higher RO design flux and a longer RO membrane life. So going back just to touch on, and I should have previously, I apologize, the life of the membrane RO, or excuse me, the life of the membranes in the UF system, the MBR, is approximately 10 years. So it's not something that's going to have to be it's not going to have to be changed out periodically. Once every 10 years will help keep the life cycle costs of the aerobic system down. So important RO wastewater design parameters, the low flux, which we talked about, the high cross flow. We want to have a high cross flow across the surface of the membrane so that we have a low chance of fouling. We have the ability to clean the RO membranes bank by bank so that we can target and focus chemical cleaning on where each bank of the machine could potentially be fouled. And then they're very resistant membranes, resistant to fouling. So they're specifically designed to treat wastewater, a little bit different than your production ROs back within the facility. So let's talk through a challenge of the RO. You're going to have the impurities removed through the RO system, but it's also going to give you a waste RO brine. So you're going to have the RO permeate. It can be reused back within the facility, but then you're going to have a brine. So how do we handle that brine? Can we get to zero liquid discharge? Because the particular stream coming out of the RO is going to be very high in TDS. So do we have to haul it? Can we discharge it to municipality? Or do we send it downstream to a thermal system so that we can look at a zero liquid discharge? If we take a look at a quick case study, this particular facility has an MBR followed by an RO. It has both ingredient water and wastewater ROs that have stringent quality requirements. So they are sending nearly 50,000 gallons per day of combined ingredient water and wastewater RO brine to a tank specifically to handle it. That particular tank is hauled off multiple times per day at a tune of nearly $7 million per year. So this particular customer is looking at a standalone evaporation system, a packaged evaporator, so that they can offset the $7 million per year in hauling and also recover additional water from the wastewater system. So evaporation can be coupled with the RO as a solution for the brine treatment and an overall reduced water footprint. We would incorporate 100% of the RO brine into the thermal system, whether it be evaporation or crystallization or some combination thereof, and will come out with between 90 and 95% of distilled water that can potentially be reused back within the facility. And you're going to have an ultra concentrated brine or even a salt substance that you have to handle from this system. So in the particular case study that we took a look at, the $7 million would be reduced to less than $500,000 of hauling of the concentrated brine stream from the evaporator, and the customer would be able to recover an additional 95% of the water. So how do we get started with a sustainable wastewater treatment project? We need to walk through the different steps so we can ensure successful project execution. First and foremost, feasibility and due diligence. We need to do some sampling. We need to understand what the constituents of the wastewater are: high COD, high BOD, high TSS, high fats, oils, and grease. Then we need to identify the technology and the process design required, complete engineering and design, and then certainly execute the project from a construction standpoint. And then at the end, startup commissioning and performance testing so that we can ensure the system was built as designed and we meet the effluent water targets throughout the system. We want to minimize the risk and optimize the outcomes for the owner. So let's look at the sustainable wastewater project checklist. Are there certain corporate sustainability goals that we're targeting? Is there a water reuse target? Do you have high sewer surcharge fees that you're looking to offset? Is there municipality or environmental regulations that is being driven by new sewer limits, BOD, COD, TDS? And do you have an existing wastewater system and are looking to add on additional green retrofits, potentially biogas utilization or water recovery through that system? So some of the key takeaways: wastewater intensification. These are various drivers that will impact the wastewater treatment facility. We have the ability for flexible wastewater treatment facility design, whether you're looking at anaerobic treatment technologies, there's multiple technologies, whether you're looking at aerobic, all the way through to UF, RO, and thermal technologies for maximum water recovery and even potentially zero liquid discharge. You need to understand the trusted technologies that you can utilize and the process that will be needed. And then we want to unlock opportunities from wastewater. We don't want wastewater to simply be a cost. We want to be able to recover the green gas and water reuse back within a production facility. With that, we appreciate all of your time. TJ, I'd like to hand it to you to wrap things up and open us up for questions.
Great, thank you so much. You've covered so much in just such a short period of time with various processes and systems. It's all about maximizing and squeezing every bit, every molecule you can out of water to be reused, and also talking about how to unlock those things when it comes times to the challenges it presents in the wastewater through intensification. So just a reminder, if you have a question, please go ahead and enter it into the box on the right-hand side. We have a few questions already, but we have a few more moments left before we close the webinar to get to many of them. So go ahead and enter that in, and we'll try to get to your question. A question that came in was related to anaerobic. I'll give this to Christina. Christina, what are the key design parameters in relation to high rate anaerobic terms of organic loading related to TSS, BOD, COD, etc.?
Yeah, no, that's a good question. So first off, we would look at FOG. We would try to make sure that that is less than 50 milligrams per liter. And that really is because fats, oils, and greases can make can kind of coat the granules and make them buoyant. You know, one thing is that the settleability of those granules are highly dependent on the FOG, and making them buoyant is not something that we like. So fats, oils, and greases are number one, and then number two is the TSS. Obviously, if the suspended solids are high, they can sometimes wash out the granules as well, right? So we want to keep our biomass inside the system, and high rate are significantly dependent upon that. And then the third thing is really the level of COD. We don't really like to see more than 30,000 milligrams per liter going into a high rate. And that's simply because the the amount of COD concentration you have does determine the granule size. And that's something that we don't want them to be too small to where it starts to flock, and then it will not settle out of those three-phase settlers.
Great. A follow-up question that came in that's related to this. When choosing between a low rate or a high rate system and a medium rate system, where's that sort of range for TSS fall for choosing to maybe switch the system from a high rate to a medium rate? Can you maybe ballpark that for us?
Yeah, absolutely. So the medium rate systems, when you're concentrating that up, you're actually concentrating not only the sludge, but also the TSS. So we like to operate at less than 1%. So you're looking at like 10,000 milligrams per liter of TSS rather than, in the magnitude of 500 milligrams per liter.
Okay, quite a lot of difference there. Another question that came in the asker said, how do you effectively manage membrane fouling in an MBR? I'm going to give that to Ryan. Ryan.
Appreciate that, TJ. So one of the important factors on managing the fouling is the upfront preliminary design engineering. We want to make sure that the aerobic bioreactor is at proper temperature. If it needs to have TSS or FOG removal preceding the reactor, we would incorporate a dissolved air flotation or a DAF system. So much of it to present the fouling is how we would handle any biological system. Make sure the food is right, make sure the temperature is right, and make sure we can offset any fouling. With that being said, there are also clean in place systems. There's also a maintenance clean, and then there's even finally a recovery clean should the membranes get even more fouled. So that is incorporated in the overall design of the system.
Great, great. Thank you so much. Another question that came in, it says, what are the most significant challenges that you may have encountered on a previous project related to implementation of a water reuse system? I know it's a pretty broad question, but Ryan, can you talk about some of the things that you've encountered in terms of economic feasibility or even culture or behavior changes at a facility?
Sure. Thanks, TJ. So we definitely want to look at what the overall goals of the project are. Are we going to be reusing the water in the facility in non-contact areas, whether it be a cooling tower or a boiler? And it goes to one of the slides that we looked at previously on how do we build the sustainability water treatment project. We have to look at the influent design parameters and, more importantly, the overall effluent goals and where that water can be reused back in production.
Hey, and Ryan, just to add to that, I think one of the biggest things is influent testing, right? We want to get good samples and we want to have a good picture of what is going to be coming down from the facility in order to fully design those pieces and parts correctly.
Excellent. Good clarification. Thank you.
Oh, an interesting question came from one of the attendees. It says, my company uses an older method of filtration post DAF, dissolved air flotation, using combined multimedia and granular activated carbon in series at approximately 200 GPM throughput. So depending on the loading through the filters, and they put an average of 78 mgl of the DAF effluent, so 78 mgl of the DAF effluent, would it be advantageous for them to replace those filtration units with a more modern UF RO system? Do you have thoughts on those kind of retrofits?
Yeah, I mean, potentially that would absolutely be an excellent possibility to add UF and RO and water reuse within the facility. We'd love to talk to you a little bit more on how we can make those modifications and what changes would have to be made in the plant. But absolutely, UF and RO can follow the existing equipment that they have so that water reuse can become a possibility there.
Great, great. Another question popped in, moving away from membranes, going back to a little bit about anaerobic and biogas. So Christina, can you talk about some of the main drivers to consider with how to use, can you talk about the main drivers to consider about biogas upgrading what's more, the user asks, what's more appropriate in terms of choosing upgrading to pipeline versus using on site, say in a boiler? Can you talk sort of that decision-making process to help clients figure out what to do with their biogas?
Yeah, no, that's a good question. It's more about what do you want to invest in capital-wise in order to make a revenue stream from your wastewater reclamation facility, right? If you look at the incentives that are out there, you buy natural gas at approximately 30 cents per MMBTU, right? But you sell your RNG into the grid at $3.30, right? And this is something that is nationally published by the EPA. They're called RIN credits. So you can imagine that the incentives that you get from producing RNG or the natural gas quality of biomethane is 10 times what you pay, right? So ultimately, yes, you can put it in a boiler, ultimately, to offset your natural gas. But at that point, it's like for like, right? You're only saving yourself the cost that you would pay to naturally, to put the natural gas into your boiler. But the upgrading actually, because of the incentives that are out there, you can actually put it into grid for 10 times that price. And that's where the economics of it come into play. But it also, because there is a standard injection skid that you have to buy from the pipeline, and you have to pipe it up, and you have to have these pieces and parts, there is a threshold. And we like to say approximately 300 CFM to 400 CFM of where it makes sense to go to upgrading, or if it's less than that, we would recommend doing a CHP or going direct to boiler.
Great. That's a good analysis of showing some positive economic options for when it comes to deciding whether to use on site or upgrade it. So thanks for that.
Yeah, and it also plays into this circular economy that everyone would like to be a part of, right? You think like your facility buys natural gas, to heat your facility or whatever, within the facility itself. You make wastewater, the wastewater produces biogas, you upgrade it into natural gas quality. It closes. Anaerobic is like the center of the circular economy.
No, that's definitely a way to look at it. It is really a transformation of waste to energy for sure. That many people are doing already, that they could also bolt on and retrofit to their wastewater plant. A question just came in too. It talks about, I have an existing anaerobic reactor that I am flaring the biogas. Is it possible to easily retrofit an upgraded system at my facility?
Yes. If there is an existing anaerobic facility, you already have the main producer, right? You already have the heart of the system. It's really just adding on those pieces and parts to now utilize that energy.
Excellent. Well, that concludes our questions for today. I have a few more follow-up slides to go through here before we conclude the webinar. Again, thanks for all your participation. Thank you for your questions. Just want to remind everyone to go ahead and take that survey post-webinar. Again, that's is tremendous feedback for us to continually improve these events for us. And of course, we'll enter you in for that $25 Amazon gift card drawing that we'll have. So at this time, if you have any questions, you can feel free to reach out to any of us. Our emails are on the screen there for Ryan and Christina. And again, just to remind everyone, you'll receive the recording tomorrow, as well as your participation certificate for joining the webinar. I hope to see you on a future broadcast to explore some of our other topics that we have. And please reach out if you have any questions or concern, or have any interest in talking about wastewater intensification or wastewater in general, or even opportunities such as water reuse. We're happy to help you through that. So again, thank you for joining us. Thank you to both Ryan and Christina for their expertise and sharing their knowledge that they have many years of experience of doing. And hope that everyone has a wonderful week. Take care.